Children, some more points for buffer action and buffer solutions. So far we have seen acidic buffer as well as basic buffer. Now children, we have one more salt which also shows buffer action but has not been categorized as acidic buffer or basic buffer, and that salt is the combination of both of them, acidic buffer as well as basic buffer, and that is ammonium acetate. Acetic acid from that portion and ammonium hydroxide provide from that portion. So this salt, ammonium acetate, also acts as a very good buffer. So ammonium acetate acts as a buffer but has not been categorized as acidic buffer or basic buffer because it shows properties of both. Hence, they have not categorized it. Here, reserve acidity is due to NH4 plus. Acidity means you are adding some base, so that portion which will react, suppose you are adding some base, NH minus, right, from any source, you are adding some base. So NH4 plus ions from here will combine with that and form NH4OH, hence weakly ionized. So again, pH is very much controlled, not much of change. And reserve basicity is due to acetate ions. Means basicity means some acid was added and this was reacting. So suppose you have H plus ions, you are adding H plus ions from HCl or any acid. So here the acetate ions combine with that H plus and form acetic acid, which is again weakly ionized. Hence here the reserve acidity is due to NH4 plus, because if you put some base, this combines with OH minus ions of that and forms NH4OH, which is weakly ionized. So hence showing acidic character because it is nullifying the effect of your OH minus ions which were added. So what will nullify the effect of OH minus ions? Some acid. So acidity is due to NH4 plus. Similarly, when you're adding some acid, so its effect will be nullified by some base. So here acetate ions, right, you adding some acid, they combine with H plus and form weakly ionized acetic acid. So in a way they are nullifying the effect of the acid added, which can only be done by a base. That's why I am saying basicity is due to acetate ions and reserve acidity is due to NH4 plus ions. And otherwise also you had seen children both the cases, if you remember, when we had NH4OH, the reserve acidity was due to NH4 plus ions. You reserve, you check it, you can go back and you can see there. And in the previous case, the reserve basicity was due to acetate ions. You can go and check. So half part of acidic buffer, half part of basic buffer, they mixed together and they found that even ammonium acetate, this salt itself acts as a buffer solution. And I repeat, you can go and check when it was basic buffer, there the acidity was due to NH4 plus ions. And in the previous case, when it was acidic buffer, the reserve basicity was due to acetate ions. So you have seen that this also shows the buffer action. One may ask you, which among the following will show buffer action or will not show? So remember, we have one acidic buffer, acetic acid and sodium acetate. We have basic buffer, ammonium hydroxide, ammonium chloride. We have third, just the one salt, ammonium acetate. So all three will show buffer action. So which will show, which will not. At least you should know these three examples, right? So answer can be all the above. Likewise. Now, pH of buffer solution, children. We can calculate the pH of buffer solution also. It is calculated by Henderson-Hasselbalch equation. It is calculated by Henderson-Hasselbalch equation. pH of acidic buffer. For acidic buffer, we calculate pH. For basic buffer, we calculate pOH. As I told you, in case of acids, we were calculating directly the pH. In case of bases, we were calculating first the pOH and then we know the formula pH plus pOH is equal to 14. Accordingly, we were going. That was what I suggested and taught you. So here, pH of acidic buffer. pH is equal to pKa plus log salt plus log base 10 salt upon acid. Active mass of salt, active mass of acid means molar concentration of salt upon molar concentration of acid. Similarly, pH of basic buffer, we calculate POH. POH is equal to pKb plus log salt plus log base 10 salt upon base, molar concentration of salt upon molar concentration of base. Now children, once you got POH, pH is equal to 14 minus POH. The formula is well known to you. Now you will say, what is this pKa? Children, I told you in the entire chemistry, especially in this chapter, the moment you have this P, it becomes minus log of that thing, like pH is equal to minus log to the base 10 of H plus ion concentration. Similarly, if I say pKa, so what is pKa? So I am writing here pKa is equal to minus log to the base 10 Ka. What is pKb? pKb is equal to minus log to the base 10 Kb. Right? This is how it is there. Right, children? So you should know these formulas. I told you simply pKa means minus log Ka. pKb means minus log to the base 10 Kb. That's how it goes. These formulas you should know. Sometimes they give you directly the value of Ka or pK. If they give you Ka, means minus log to the base 10 Ka. If they give you pKb, you can put directly, but if they give you Kb, minus log to the base 10 Kb. So these were your formulas, children. We will be doing questions based on this formula. Right now these formulas are there, and this equation is known as Henderson's Hazelbatch equation. And I repeat, when we have P, especially in this formula of whatever, so it is minus log of that, like POH, minus log to the base 10 OH minus ion concentration. pKa minus log to the base 10 Ka. pKb minus log to the base 10 Kb. So you have seen some of these important points. Definitely important, not difficult, but yes, learn with proper understanding so that you can answer your short questions, multiple choice questions, fill in the blanks, as well as simple numericals. So I hope it is clear to you. I stop here. There's no point in repeating it. You need to give time in the evening and do see it very attentively, and it will be clear to you. So for this video, we stop here.